All right, so here is, we've reached a point, I think, where I feel comfortable talking about this really complex thing that I've made here. This is a mind map, right? This is, I like mind maps because it helps me write down everything that I know so far, or at least some of the things that I know so far, and put everything with all of that information within the context of each other. So this is a mind map on quantum field theory, quantum electrodynamics, and quantum chromodynamics. Right? We're gonna get really, really deep into this stuff, and some of the stuff we've gone over already, and most of the stuff we actually haven't. Right? I'm gonna walk us through this mind map briefly to see what is to come and what I intend to go over. Right, there's a lot to go over here. I have no time constriction or no time constraints on myself, and this is just again, this is just not even, this might not even be a portion of what we cover, because I really, really want to go over this, and because again, QFT, QED, QCD, this is all really interesting stuff to me, even though my life has been in the life sciences and biophysics. This has been something that I've been studying on my own time, and because I think it's really, really interesting. And again, I apologize for those of you who are interested in biophysics more than this, because I don't have many videos on that yet in that playlist, but I will. I'm sort of in this zone right now on quantum, so we're gonna keep on going with this. But what we have here is we've started off with the Schrodinger harmonic oscillator, right? And we did this reparametrization, and we defined our creation and annihilation operators. And from all this, we came to our Schrodinger harmonic oscillator in this form, right? And then we briefly talked about number operators. We talked about these important algebras, or these important commutation relationships, through this canonical relationship right here, where P is a canonical momentum, the quantum canonical momentum for the canonical position points, right? The Q is a proxy for position, and the P is going to be a proxy for momentum, because this is the derivative with respect to Q. Right, so we've gone over a lot of the left side of this. Right, and I'm gonna zoom in a little bit here. Actually, I won't be zooming. I want to put this all in context as we're going through this. I haven't really quite touched on the number operators quite yet, because I haven't done that yet. And I have, okay, and then we briefly started going over relativity, right? We went over, this is a relativistic energy, and we have this. We have this relativistic energy, and when we combine that with our quantum operators, we got our Klein-Gordon equation. And then from the Klein-Gordon equation, we're going to diverge a little bit more, and we're going to start talking about the Dirac equation, right? I don't really know when I'm going to start talking about the Dirac equation, but you can see right when we start talking about the Dirac equation, this is going to take us down multiple routes, right? We're going to be able to investigate spin a little deeper. We'll also be able to investigate spin through angular momentum analysis, right? All of this right here is angular momentum analysis, where we can figure out the commutation relationship between this right here should be oh geez, that is a very thick pen. Oh, the spinning wheel of death. Would you look at that? Okay, but this is a commutation relationship, and all of this, right? All of this is analysis of angular momentum, where we find eigenvalues for our angular momentum operators and our differential operators there. And then I'm going to make that there's our commutation relationship. And we're going to find some intricacies within this analysis within this analysis where we're going to have to introduce spin, right? And then when we introduce spin, we can tackle spin again, and we can bring this. There's connections between here and here also, right? So when we get to our spin, we're going to be able to see what our spin matrices look like. We're going to be able to see what exactly do these spin matrices act on, right? These spin matrices act on things called spinors. Spinors are quite interesting objects, and we're going to take a lot of time into really looking at these spinors and trying to understand exactly what they are. Although understanding spinors, again, I can't remember where I heard this from, but understanding a spinor is akin to not understanding it. If you think you understand what a spinor is, then you don't know what a spinor is, right? These are really mysterious objects. But nevertheless, they're crucial and they're important in quantum field theory, quantum electrodynamics, or quantum QED and QCD. And then from the spin analysis, we're going to be able to identify a couple of objects. We're going to be able to identify Weyl spinors, dual spinors, right? There's a lot of intricate mathematics that goes on into understanding these objects, right? And I don't have anything here, any equation here for the Weyl spinor, but I do for the dual spinors, right? Dual spinors are sort of somewhat equivalent to they're sort of somewhat equivalent to like a dual vector, right? But it's a spinor, right? It's not a vector. And we're going to be able to identify dual spinors in their relationship to scalars, vectors, and tensors, right? And this is going to be that's going to be a couple of videos probably in themselves, because this is a very interesting field of study, right? From the Dirac equation, we'll also be able to talk about Lagrangians, right? So right when we get the Klein-Gordon equation and the Dirac equation, we can start talking about Lagrangians. And we also have the Proca equation, right? The Proca equation is something I haven't really written down here. I'll write it down just Proca equation. And we're going to be able to take a look at the Lagrangians that sort of give birth to these differential equations. Because once we have a Lagrangian, right? Once we have a Lagrangian, then things get really, really interesting. Because remember, Lagrangians tell us a lot, right? We haven't really gone over them in their details yet, but Lagrangians, they tell us a lot because it tells us hidden within the Lagrangians are all of the differential equations of motion that govern the dynamics between systems. And from the Lagrangians, we'll be able to investigate gauge transformations within these Lagrangians. And here's a non-abelian gauge. This is sort of non-abelian gauge theory. And this is so non-abelian gauge nag. Yeah. And so there's this huge investigation on spinors and spin and these Lagrangians. And we're going to see how exactly these are related to QFT, QED, and QCD. Same thing with this analysis here. This is analysis of angular momentum, like I've said before. Once we get spin, we'll be able to take a look at the addition of angular momentum, the general commutation relationships for angular momentum, and the Clebsch-Gordon coefficients. We're going to talk about. I'm going to hopefully talk about those as well. Now I have this whole right end of this mind map here that I haven't talked about, right? So Lie algebras, we're going to want to talk about Lie algebras. We're going to want to talk about Clifford algebras. We sort of kind of talked about Lie algebras already through commutation relationships, but I want to talk a little bit deeper about what these Lie algebras are and how they're different from Clifford algebras, right? Lie algebras are usually denoted with the brackets comment there. Clifford algebras are usually denoted with these kind of squiggly brackets. And from understanding these, we're going to be able to understand generators and rotations in multidimensional spaces, transformations within those spaces, the generators that exist within those spaces that are associated with these interesting transformations. And we're going to also be able to define closure. And this is going to lead us into a couple of areas of topology, and many other different types, a set theory and all that kind of stuff, right? When we talk about closure, that's a term that's often thrown around in set theory and topology. But abstractifying this math is going to lead us to some interesting notions, right? The metric also, I've talked about how the metric affects quantum topological quantum field theory, right? So that's going to be an interesting area to study as well, and we're going to talk about how what topological quantum field theories look like, and so again, so this is a mind map. This is not the mind map, right? We can blow this mind map up into more details that get us from step to step in this whole thing. But again, I didn't want to overcram it too much. You could see I started big over here. I didn't think I was going to need the whole slide. But then as I started adding more and more to this, I had to start to figure out what I wanted to leave out of this mind map and what I wanted to put in the mind map. But again, by no stretch of the imagination is this it, right? The quantum field theory, quantum electrodynamics, and quantum chromodynamics, these are very rich areas of study. And we're eventually going to be able to talk about, when we start invoking spin, we're going to eventually be able to talk about the Wheeler-DeWitt equation. And this is going to, this is an interesting equation because this is, let's see, I'll box this in. This is an interesting equation. Once we start talking about, especially spin, let's see, I want to make this a different color. I'll make it red. Once we start talking about spin, then this is going to take us to GR. And I'll say general. Right, general relativity. We're going to talk about the Wheeler-DeWitt equation. We're going to talk about other attempts to take all of quantum, right, into GR. And this, for me, is more or less of theoretical hobby, right? This finding the actual connections between quantum mechanics and general relativity, that's difficult, right? This is a study that's been going on for a really long time. This right here, and this right here also. This right here, that connection right there. This is difficult, right? We're going to be able to talk about it a little bit, but by no means am I an expert in this. With all that being said, I don't want this to go on for too long. So we have all of QFT, QED, and QCD in somewhat of a mind map, right? This is all. This might be very overwhelming, a lot of equations to look at. But as we go through it, we're going to go through it slowly. We're going to talk about the intricate details within this mind map. We're going to be able to make many of these transitions. and be able to investigate a lot of this as well. I also don't want to shy away from condensed matter physics, right? You can hear ambulance outside. Matter physics, because there is a lot of stuff a lot of quantum that goes into this as well, and semiconductors and stuff like that. So yeah, here it is. Here's the mind map, and I don't want you to hurt your ears with that with that noise of the ambulance going by. So I'll stop right now, and I'll see you guys in the next one. Thanks for watching.